we will be looking at trigonometry, translation, yes, transformational, geometry, yes, we'll be looking at that. And so we expect you to participate. We expect to hear from you, and just feel free to participate in the chat and to open your microphone and speak, especially when you are identified. Use the raise hand feature so that the coaches who will be taking you through this afternoon's session can know what it is that you're thinking or what is on your mind. And so to take you through this afternoon's presentation, we have Mrs. Karima Mundell Thomas and Mrs. Neva Cameron Edwards. Yours truly is Faithlin Williams. I am a math coach working with the Ministry of Education, and we do have other math coaches online who will be here to facilitate questions that you will ask. So you have a plethora of persons who will be working with you this afternoon. So welcome to our session. Over to you now, Mrs. Neva Cameron Edwards.
Thank you very much, Mrs. Williams. Good afternoon, everyone. Guys, are you seeing my screen? Everything up? Are you seeing the?
Yes, we're seeing it.
Okay, thank you. So thank you very much, Mrs. Williams, for per. And again, we are in another series of workshops as we support you in this CSEC coming exam. So as Mrs. Williams would have said, we have three main presenters. She's also with us today. We have Mrs. Mundell Thomas, as was said before, and Mrs. McNeil Darby. So let's go through what are some of the things. Oh, before we go to that, today we're looking at transformation geometry with focus on translation and rotations. Now, here are a few things that we want you to grab before we get into today's presentation. Make sure that you have something to write with, your math book, your calculator, graph paper, and especially for today's session, yes, for today's session, you'll need your geometry sets and your pen and your pencils. So we're going to give you 2 minutes to go and grab these. By now, you would have gotten accustomed to what are the instruments required, so you should be ready to go. All right, so the aim of today's session, we'll be looking at translation and rotation. But as it relates to translation, we're going to be looking at how do we represent, say, or how do we look at a translation in a plane using vectors. 2, we're going to be looking at determining and representing the location of the image of an object, as well as given the image, look at the object under a particular transformation, whether it's rotation or translation. We're going to be looking at the relationship in terms of similarity and congruency between the object and its image. And the final thing we're going to be exploring today is how do we describe a transformation given an object and its image. So by now, you'd have gotten your instruments and we're ready to go. We're going to take you through an activity just to make sure that you are comfortable in the session, to relax. And I'm going to invite Mrs. McNeil Darby to take us through this activity, the icebreaker. Mrs. Darby can go ahead and unmute.
Yes, good afternoon, everyone. So this afternoon, we want to be looking at the magic square. And a magic square is a square that is divided into smaller squares, each containing a number, such that the value in each row, column, or along the diagonal will add up to the same magic constant. Whether you're adding up across or down or diagonally, the result should be the same. And the staircase method is one way to create a magic square. So we're going to look at how to create the magic square using the staircase method. We start with the number 1 in the middle cell of the top row, and the next number is placed diagonally upwards in the next cell. If that cell is occupied, then we place the number immediately below the original number. So these are the rules of how to create the magic square using the staircase method. If your number lands in a cell in an imaginary square outside of your magic square, you find where it is in your own magic square by matching the location it was in the imaginary square. So we want to now go ahead and create a 3 by 3 square. You can draw your 3 by 3 square like what we have there, with the 1 in the center cell at the top row. So go ahead and draw your 3 by 3 magic square. Let's go. Go ahead. In the interest of time, we are putting in 3 numbers, the last 3 numbers, 7, 8, and 9. Towards the end, you'll see if these actually fall exactly where they should fall. So draw your square, and you may put in the 7, 8, or 9, or you can leave it, but definitely put in the 1. All right. So let's go. All right, so remember we say start with the number 1 in the middle cell of the top row. Remember the rule now, the next number, which is 2, is placed diagonally upwards, which would be 1 place to the right and 1 place up. All right, so where would we put number 2 then? Right there. What do you notice? You should notice that the number 2 is outside of our magic square. So what will we do? So we call where it is now, we say it's in an imaginary square. So what should we do? There is a rule for that. Since the number 2 lands in a cell in an imaginary square, which means a square outside of our magic square, we will find its location in our own magic square. So let us describe where the number 2 is in our imaginary square. I know you have thought about it. All right. Do you notice that it is in the bottom row and to the very right? So we'll put it right there, bottom row, extreme right in our own magic square. Find the location in your own square and put it there. All right. So let's continue. So we are putting the numbers 1 and 2, and we said that 7, 8, and 9 we are given as bonus at the start. All right, so now we know where 1 is and we know where 2 is. Remember, each time you use the last number you place to find the next number, and the positioning is the same. The next number, which will be 3, is placed diagonally upwards, which is 1 place to the right and 1 place up from 2. What do we notice again? Where would 3 be? 1 place to the right and 1 place up. So where is 3? Have you put down 3? Is it in the square or is it in the imaginary square again, in another imaginary square?
So Mrs. Darby, you want to give them a chance to tell us where they would want to place it in the magic square. Let them know that we want.
Okay,
yes.
All right then. Okay, so you can type in the chat, describe where is the number 3 now. You can type in the chat. Can anyone tell us where you're seeing the 3? We're starting where 2 is. We're going 1 place to the right and 1 place up. Where is the square? Where is the 3? Anybody want to tell us? Describe where it is. Yes, 1 place to the right and then 1 up. So where is that? Is it in our existing square or is it in an imaginary square again? Any thoughts? opposite the 2. I hear opposite the 2, and some persons are saying it's in an imaginary square. Is the imaginary square to the left of our existing 1 or to the right? Where is it? And where exactly is that 3? Right, it's in an imaginary square to the right. I hear Kimoya saying imaginary square to the right. Where in that imaginary square is it? All right, let's look at it. We all agree that it is in an imaginary square to the right of the 2. Okay, so we now examine that imaginary square and see where the 3 is. I think I would say it's on the left of the square in the middle. So we'll find that location in our own magic square. So we'll put in the 3 right there. It's in the middle on the left, in the left column. All right, so let's go again. Starting at 2, we go 1 unit to the right and 1 up. The 3 goes there, but the 3 is outside of our square. It's in an imaginary square. We find where it is in that imaginary square and put it in that same position in our original square. All right, so we have 3. Let's continue. Okay, so we're still putting in the 7, the 8, and the 9 because we are giving these as bonus values. Later on, we'll see if it actually matches up. All right, so now we're going to do 4. So we're going to start with where 3 is, and 4 is to be placed diagonally upwards, 1 place to the right and 1 place up. What do you notice this time? 1 place to the right and 1 place up. What can you say about where 4 should be placed? Correct, I agree with you, number 13. Yes. Same place as 1. Is there a rule if there's a number there already? Yes, there is. If the spot is occupied, then the new number is placed immediately below the original number. So I'm going below. So going horizontal, vertically, I'm going vertically, and I'm going down. So 4 is immediately below 4. Listen to those directions. So that's where 4 is. Okay, on your magic square, I would like you to place number 5. And 5 is to be placed diagonally upwards, which is 1 place to the right and 1 place up from 4. Can you tell me where I should put 5? You can type in the chat, where should I put 5? Below 1, yes, that's one answer. Larissa, thanks for that. Anybody else? Below 1 is a good description. I know exactly where you're talking. Can anybody else describe where 5 is other than saying it is below 1? All right, we'll go with below 1, and I like the direction. We are talking directions, left, right, above, below, and so on. All right, so 1 place to the right and 1 place up would put 5 there. And then can you put in 6? Where is 6? Describe where 6 would be. 1 place to the right from 5 and 1 place up. How would you describe where it is? Anybody want to try? To the right of 1. Yes, we're getting our directions in. To the right of 1. Kimoya, thanks for that. And number 13, thanks for that. To the right of 1. Okay, so 6 goes to the right of 1, which is 1 place to the right and 1 place up from 5. Let us look at where 7 should go. We're not going to reveal it just yet. So number 7 should go 1 place to the right and 1 place up from 6. So where would it be? Notice that it would have landed where 4 is. It would be in an imaginary square over there. So it should land where 4 is. So what's the rule? If it lands where a number is, you write it immediately below. So 7 would go where below 6. And then you can afterwards figure out why 8 is where it is and why 9 is where it is. So we can reveal them all. Okay, so we have been talking directions. We have been talking about how the numbers are. I would like you to describe for me the ones that really you didn't have to do any adjustment, which would be 4, 5, and 6. How would you describe the positioning of 4, 5, and 6? Describe for me the positioning of 4, 5, and 6 since it's revealed already. Anybody want to take on that one? The positioning of 4, 5, and 6. Any descriptions there? I hear diagonal. Diagonally counting, yes. Anybody else? All right, those are the words I had in mind. I had diagonal in mind. I had slant in mind as well. All right, they're in a diagonal line. Thank you, Kimon, sorry, Dane, and number 13. Thank you for that. All right, so as I said, we have been using the staircase method to create our magic square. You can use the staircase method to create a magic square. Remember, you could get the magic constant, which is the sum of the row, column, or diagonal. You don't have to start at 1. You start at any number you wish, and then you do the next number after that. So if you want, you could start with 49 where 1 is and follow the directions, and you get a magic square. You can play that game with your friend. All right, so we have been talking directions and so on. I'd like to hand over to Mrs. Cameron Edwards, who will take you through the first part of the presentation on transformation geometry. Take it away, Mrs. Edwards.
Thank you very much, Mrs. Darby. And I hope that activity would have allowed us to look at the different movements. I noticed the words diagonal, to the left, up. Those are some of the terms that were coming out of the discussion, rich discussion. So I'd like you to know, place in the chat, so type in the chat, when you think about the word transformation, what comes to your mind? So if I'm asking you to tell us, what do you think is a transformation? When we talk about transformation, what are we talking about? All right, I'm seeing some persons posted in the chat. This is Darby. Could you assist me here?
All right, so persons are saying that it's to change, to modify. Brianna is saying modify. Blade said change, and 13 or 3 said to change.
All right, wonderful. So when we think about, the movie Transformer, I know many of us would have seen that. We noticed that, one of my favorite car in the movie, Bumblebee, we're realizing that they're changing. So I love the terms that are coming out. So let's think about transformation in geometry. It refers to a movement of an object in a particular plane or coordinate system. We have 2 coordinate systems, but today we're looking at the Cartesian plane, the 2-dimensional system. So transformation occurs when there is a change in position, shape, or size. So some of these came out, and we wanted to take off the notes, whether you want to screenshot it or if it is that you want to scribble it down quickly. And we are also live on YouTube. So if you didn't get a chance to write off something, or you want to even look back at the magic square, you can always go back to our channel, Region 1 channel, and you will find this presentation there. So when we're looking at transformation, it speaks to about a change in position, whether it's the shape or it's the size. We're going to be exploring some of that today. Now, as was mentioned before, we're going to be looking at the 2-dimensional coordinate plane. You're going to see a lot of this. We're going to ask you to do some graphs. So make sure you have your graph papers with you. We want to remind you of our vertical number line, which is our y-axis, as well as our horizontal number line, or x-axis. And both number lines actually intersect at the origin at the coordinate 0, 0. Now, today, as you would have pulled from the game, because I am realizing that throughout one of the instruction, and that was in the magic square, is that they were moving to the right 1 unit and up 1 unit. So when we talk about translation, we're going to now explore this. In the chat, or if you indicate, we'll allow you to unmute. You're going to look at this image here, and we have an example of a van, and the van would have moved from location A to location B. How would you describe the movements of this van? You can do so in the chat.
Nothing
So
yet in the
nobody.
chat.
So we're looking at van, the car or the van at location A. How do you think the van would have moved from A to B? Mrs. Darby, how do you think the van would have moved? We could have pushed it.
I think you could push it. The distance not so far that you drive, so maybe you'd push it.
We could push it. All
And
right.
in the chat, Mrs. Cameron, in the
Yes,
chat,
yes.
N3 is saying it's a forward movement. And then Kimon Williams is saying the car is traveling to the right.
Okay. All right. I love the description. So let's see something in motion. All right. So we all saw the motion a while ago. And based on what we would have gotten from the chat, we'll agree that the van moved along. Well, we didn't hear the word line segment, but we're helping you. We're warming up. So the van moved along a line segment AB directly to the right. So now that we would have actually gone through this one, I'm going to give you another one. And then I'm going to ask you to describe the movement. So let's look at this second example. So in this example, the shoe is moved from location A to location B. How would you describe this movement? How would you fully, we did say that in one of the objectives that we're going to look at how to describe transformation. How would you describe this movement?
I think they're typing, it will soon come up. What they're
All right.
saying. I think we just give them a little time to.
I will give them a little time before I do anything. I want to hear how they would describe this movement.
I wonder if it would involve a straight line of any sort. Can we use a straight line to describe this one? Look a little ticklish to me.
All right. I wonder if I should allow it to do some kind of movement, and that would help them with the description. Let's see. So while you're there thinking, I'm going to do something. We are saying that this movement can be described as a movement along a slant line, but we are further going to describe it as a shift to the right and then down. Let us see what happens with the shoe. Do you agree with that statement?
So I think both descriptions make sense. It could have been just that you slide it along the slant.
I was hoping to see if anybody was going to tell us that, they walk in the shoe slantly, or something, but they're warming up.
They're warming up.
Yes. All right. So when we're looking at shoe A and we look at the components, this one was a little bit different from the one before. We are now seeing two different movements. We're seeing a movement to the right and we're seeing a movement downward. All right, we're going to explore it a little bit more. But just before we go into that exploration, who can remember what Mrs. Darby would have said in the magic square? There were some specific movements that she shared about each point. When we looked at the position of the 4 and the 5, what instruction did she give us? Anybody remembering? Come on, man, in the lively up, man. Nobody remember what she said in terms of the movement from 4 to place the 5 in the magic square? All right. I remember that she said move 1 unit to the left and then 1 unit up. She didn't actually say it like that, but we are now going to talk to you about
1 unit to the right.
To the right and
Right,
1
and
unit
then 1
up. Thank you. So when we
somebody
talk
said
about,
diagonal.
somebody said diagonal. All right.
Okay.
But while she said the diagonal, because I remember the last statement spoke about the diagonals, but now we're going to be looking at describing the transformation a little bit more in detail. So when we talk about the translation vector, we're now putting something here for the very first time, and we want everyone to take this off because we're going to be using this information throughout half of the presentation. So the translation vector AB shifts the object A units horizontally at the left or right, and B units vertically either up or down. So just think about the instructions. What could be the translation vector? What was the movement given? I'd like some numbers coming up in the chat. What did she say? How much units to the right and what unit upward? What could you give us from that task? Nobody remembered? I think somebody just wrote something in the chat. Yes, 1 unit to the right and 1 unit up. So A here would have been 1 and B would be 1. All right, so make sure we have this information because we're going to explore it a little more. Now here I have a frog, and the frog is at a starting point. And I want us to spend the time.
Mrs. Edwards, somebody was asking you to repeat what you just said.
Okay, so when we talk about the translation vector, I wanted us to come up with something similar in the form of a vector to represent the movement that you would have done in the magic square. Did anybody write that movement in the chat? So that's what I was asking. How much units to the right did you actually move or was instructed to move, or what was the movement vertically? Did anybody get to write that down? If you did not a problem. In the next activity, you're going to spend a little bit more time writing down some translation vectors. All right, so here we have, a frog. So Mr. Frog is sitting here at the starting point, and we're going to describe the movements of the frog. Now, there are some things that I want you to describe or to say in your description. I want you to, one, tell me what transformation are you seeing being done here, because we want to practice so that when we actually get to our CSEC questions and we're answering the questions, we can describe the transformation fully. So we're going to be looking at the first set of jumps by the frog. Okay, in the chat, I want you to now tell me what is the vector, or describe the movement. Can you describe the movement from where the frog was to where the frog is now? I'm going to give you some time. So we're practicing, we're using this activity to practice how we write or to describe movements.
Nothing in the chat yet. I'm wondering if the consideration, oh, someone did it very well. Kimoya says 3 units to the right and 2 units up. And Larry said the same thing. And Kimoya again, 3 units to the right and 2 movements up. 3 movements to the right and 2 up. Someone else wrote translation and attempted to do the vector 3, 2, J.
All right. So I did ask you to say what transformation was it. So the person who described it in detail, not that the others are incorrect, but when we're asking you to describe and we want to practice this. So yes, it's a translation, but what would the vector look like if we were to write this vector 3, 2, or 3 units to the right, up 2 units? What would that look like? How would we write that? I believe Mrs. Darby said someone would have penned it. You might not be able to, in the chat, to write it as how I have it here on the screen. However, when we're talking,
did it, you know, Mrs. Edwards,
did it?
right?
Okay.
Yes, 3 at the top, 2 at the bottom.
Fabulous.
Did it as well.
Okay.
Others said it, but Laris and Kenardo actually did it. and some others have been doing it.
All right,
Yes, we have been
wonderful. So when we look at 3 and 2, it tells us the horizontal movement and the vertical movement. All right, beautiful. Let's see now, look at where the frog is. The frog is going to move again, and I want you to quickly in the chat state 1, describe the transformation as well as state the vector that is represented.
So they're to tell the transformation and do the vector.
Yes.
That's what we want. Okay. Mhm.
So did we see that? Let's go back. So we're here
At the blue spot.
at the blue spot. And now we're at the yellow spot.
So they're writing the type of transformation and then further describe. Okay, Kimoya says it's a translation and she has 2 at the top, 3 at the bottom. Blade is saying 2 to the right and 3 down. Kenardo says translation 2 units to the right and 2 down. And Jay says translation 2 minus 2.
All right, so we got so many things. First of all, we got 2 to the right and 3 down. All right, let's look at the jump. If we were to start at the blue, did you say 3 or we didn't have any 3?
No, I don't remember seeing any. Right, some persons were saying 3.
Right,
yes,
I am sure you said that first.
Okay.
And why I want to identify that at the start, remember now it's when the frog, or when even you're counting on the Cartesian plane and you're looking at your each centimeter literally have to move 1. So we don't count the start. And you know, Mrs. Darby and lots of our students tend to have that error. They start counting from the starting point. So while they did it beautiful for the horizontal movement, 1, 2, there are some students now who will begin to count from this initial point, and that's how they would get 3. But it's really 1, 2 to the right, 1, 2 down. Now I heard some students saying down, but I heard one particular, or based on what you said, one student gave us this translation. They gave us 2 and -2. Now, students, I want you to type in the chat, what does this -2 tell us? Because we're talking about the direction. We know that there's a horizontal shift to the left, to the right, vertical movements up or down, but we need to know, because notice in our 2 vector or column matrix here, we're not putting the words left or right, but something must tell us what direction we are going in. And hopefully by now you would have recognized that if we are going to the right, then the value of that number is positive. So if we are going down, then we are seeing here that is represented with the negative sign here. All right, beautiful. So we're making.
So Mrs. Cameron Edwards, you're
Yes.
saying that if it were 2, then it means I would be going up. That's it. The second number means I'm going
Exactly.
up.
So if
But
we were
-2, go ahead.
go ahead. No, that's fine. You can continue.
No, man, you go ahead.
Okay, so if it is that we were going upward, then it would have been a +2. And now that since we went down, it's now -2. So let's see how you can quickly, now we're putting it all together.
There's someone else speaking. Kimon is saying,
okay,
this might need some clarification. It tells us that we passed the x-axis and has gone downwards to the y-axis where the numbers are negative. I think that needs a bit of clarification.
So remember, this is not a Cartesian plane. I see where you're going in your thinking. However, this is just movement, left or right. And remember, I'm going to also bring it back in the next slide for those persons who are joining after. When we're looking at the vector, the horizontal shift is to the left or to the right. So if you're moving to the left, it would be negative. And if you're moving to the right, it's positive. So this currently here is not speaking to the Cartesian plane because we don't have a X or a Y axis here. We have not drawn that here. This is just something that is a free position But remember, when we're looking at vectors, we can have three vectors, which speaks to the direction in which we're going. So
So
in
it's
this
just from
case,
where I am.
it's just from where you
So I
are.
was at the
So,
blue spot,
and
and I
we
moved
two
to the
units
right
to the
of the blue
right,
spot, and
right?
then I moved down from the blue spot
Exactly,
rather than the Cartesian plane.
than the Cartesian plane.
Okay, okay.
All right, I'm glad for that question, because there are some persons who might come on YouTube, see us having a discussion and still thinking that the reason why, or they're seeing an imaginary X and Y axis that is not there. We did not label anything. We're just moving left, right freely. But we are saying to you, the direction tells us. So if it's positive and we're looking at the horizontal movement, we are moving to the right. If it's negative and we're looking at the horizontal movement, we're going to the left. If we're looking at the vertical movement, which is all the one that is in the bottom of the vector, we are moving up or down. So if it's up, then it's a positive movement. And if it's down, it's a negative one. So we have two more to go. So let's look at the frog jumping one more time. Now that we have had this beautiful discussion, can you now write in the chat? Remember, we're describing the movement. We want to say what transformation is it, and we also want to give the vector. The reason why we're also talking like this, we want you to have an idea of the different transformations. Today, we're looking at two, and later in the week, we're going to share another feed, and you will see the other two transformations. So we want it to be clear. So state which transformation we're looking at and the vector that speaks to the movement of the frog. Come on now, the chat should be lighting up.
In the
So,
chat, one
yes.
person said just one, just a number one, just one number. And 13 says, I see one at the top and three at the bottom. Bevane says 1, 3. I think he can't get to line it up. Kimoy says translation, very good. 1, 3. Kalisha is saying 1, 3 as well.
All right, so many persons are still leaving out the part where you're describing the transformation. So remember, we're asking you to practice describing the transformation, name it, and then give the vector. All right, so agreed. Yes, it's a translation, and the vector is 1, 3. We've seen one jump to the right, one unit to the right, which is positive, and we're moving up 3 units, which is positive 3. Now, for the very last jump, I want us to look at how the frog is jumping. Now, by the way, look at the position of the frog. Where do you think the frog wants to go? Let me just ask. Where do you think the frog is aiming to go? No one wants to take it off. You don't know it. All right, not a problem. Okay, one person is brave enough.
To the right.
To the right, okay.
Forward, some says to the end.
Okay, all right, let's go. Let's see. So the frog is about to go. Now again, for this final jump, I want you to describe the transformation as well as the vector that supports this movement.
Some persons jump the gun to say what they think it would be. So Enrique, you can now go and type in what he actually did, what the frog, Mr. Frog actually did.
Okay.
There's one answer already in the chat. Jay says translation, -4, -3. Kenardo says translation, 4 to the left and 3 down.
Okay. You're playing it smart. Okay. Anybody else? All right. So we can go, we can wrap up
I'm
with this
seeing
one.
N13 is saying -3, -4.
Okay.
And translation, and Dane is saying -4, -3. So Dane and N3 agree that it's a translation, but the numbers are reversed. The number at the top is at the bottom. They're both saying that the numbers are negative, but for N13, he's saying the -3 is at the top.
All right. So I love that discourse, very rich, and I'm liking the fact that here, two persons can banter whether or not it's -3 first or -4. Now
Beverly
remember,
say -3 is first.
-3. Why do you think it's -3? Is it because that's the initial movement, or is there a way in which we write vector or write our vector components? Is there a specific way? Is there a specific direction that we're to see or to record first, even if the jump or the movement is not showing that? Is there a specific way in which we ought to write our movements?
Is that the AB that was mentioned earlier that they should
Yes,
have
it's
copied from the
AB.
screen?
Yes. So if you did not get to write down the vector component and what it represents, it's going to be coming again in the next slide. But remember, in our discussion, we said that we have to do the horizontal movement first. So we have to, even though the frog actually jumped down, we have to write the horizontal, which this case, the frog went to the left after jumping down. So the correct way of writing it would have been -4, -3. And that's another error, especially when you're doing multiple choice. You will see the flip. You will see -3, -4. But we want you to understand that when we're writing our translation vectors, or when we're writing our vectors and it's describing a translation, it's the horizontal shift first, left to right or whichever one, and then we describe the vertical movement. All right, so to my students that are thinking and clicking, can you now look at all these movements that we have here and give me the total, all of what the frog just did? Could you find the sum of all of this? And can you use the diagram to help you to see all of those jumps that the frog was actually doing? This is our total.
So you want the movement from the start
to the end,
to where it finally is right now?
Yes.
Okay.
So we're going to give you like 2 minutes to look at it. Look at all the movements. They're all listed on the right. The initial movement, 2, 3, then 2, -2, then 1, 3, then -4, -3. So from start to finish. Okay, I think some persons are now writing in the chat.
Okay, I see Jay says 60. Kenardo correctly says it's a translation, and he says 2 units to the right and 0 units up down.
All right.
Jay did not say what kind of transformation it was. Whether I think he would assume that we believe it's a translation, but Jay, you need to practice saying what it is. Kenardo is 2 units to the right and 0 units down.
All right, so let's put it all together. So we're gonna sum the first vector to the second, to the third, to the fourth. And then we're gonna write it as an addition of all these vectors. So let's look at the sum of the horizontal shift. We're looking at the shift, and I want to say this until we move over and we're talking about the X and the Y. So let's look at what we have here. So you said somebody gave us what? 2, 0. Let's check if that's correct. 2, 0. And then I'm going to ask a question. What would the 0 represent? But let's check to see if that answer is correct. So when we add 3
there's one
plus
person,
2.
Mrs. Edwards, there's one person with just a single number, the number 2, rather than 2 numbers for the answer.
And that's fine.
Quite a few saying 2, 0.
All right, so let's look at it. So we have 2 plus 3, that's 5, plus 1, that's 6. When we take 4 from 6, we're left with 2. And for B, or speaking of our vertical movement, when we sum all of them, we have 2, and we're subtracting 2 from that, that's 0. We're adding 3 to that, that will give us 3, and then we're subtracting 3 from 3, we're left with 0. This is now what we have. Now, there are several students who gave us 2, 0. What does this vector tell us? 2, 0. Can anybody tell us what this vector tells us? And can we look on the screen and look at the starting point and look at the position of the frog at the end and see if that is corresponding to your discussion or what you're sharing.
So I think you're
All the
asking
person, yes, thank you, Mrs. Darby. So for all the persons who wrote 20, what is 20 telling us? Or why did you, yeah, okay, let me give you some time to think about it. And the
So
student,
movement to the right.
okay, Tashel, go ahead, you said? You said 2 movements to the right, but what does the 0 tell us?
Miss 0 would have been like for the y-axis, they would move.
why.
All right, so I'm hearing us saying y-axis. Remember, we don't have the Cartesian plane currently. We're just looking at movement to the left, right, up or down. So
Canardo has something.
go ahead, Canardo.
It says there's movement to the right, but no movement up or down. Jay says the frog went two spaces to the right, and the y-axis stays constant. Mrs. Edwards is talking about the y-axis. There's no y-axis. There is movement left or right, up or down. Devaney says the frog made 2 movements to the right and made no movement down.
All right. So let us check on our friends on YouTube. We don't want to leave out our YouTubers. So YouTubers, you can go ahead and type in the chat, and then we will also have someone share so that you can be a part of the discussion. So indeed, let us look at this. So from where, so even though the frog did all of those jumps, go ahead. Go ahead, Mrs. Fenton.
Okay, so there were a few comments in the on YouTube. They were answering about when you were talking about the original translation.
Right.
There was ECHIS, Aegis had commented that it was 3-2 from the very beginning. So I'm sorry that I didn't say that. Tamara White had said good afternoon to everyone, just to let you guys know. So YouTube is there and going. Wizzies also participating, saying 3-2, and they were no immediate comment with it.
All right, thank you very much, Mrs. Lodge Fenton, a member of the National Mathematics team over there on YouTube. All right, so we're gonna see this vector 2, 0, or another one with 0. But like someone would have mentioned, as Mrs. Darby is saying, we're not yet using the Cartesian plane, so we don't want that description as yet. When we're dealing with the Cartesian plane, we will speak to that. But you don't even need to say y-axis or x-axis. In our description,
just movement.
It's just movement. So we're talking about, you wanted to say something?
I just wanted to point out that the 2-0 looks so real to me. I can see that from the start to where the frog is. It's 2 jumps.
2 jumps alone. There was no up and down. So that's why that's 0 there.
And we did the calculation and it come out same way.
Same way.
So amazing.
So the student that wrote 2 alone, then they would need to understand that even if there's no movement in a particular direction, you have to still use a 0 to indicate same. All right, I think we have explored this, so we can move on. Again, for those persons who are joining and did not take off this particular notes, please remember we're asking you to screenshot or to write it down. That when we're talking about the translation vector, it speaks to, or the vector itself, it speaks to a horizontal movement, left, right first, and then the vertical movement up, down. All right, we are now going to explore GeoGebra. All right, so in my GeoGebra activity, we're going to explore a few things. I have a point, B, which is my starting point, and you're going to see my object here on the screen, and you're going to see my coordinate for A. Don't worry about the A prime. I'm hiding my image behind it, so we're not doing anything as yet. So we have 1, 2, that's my coordinate. So those persons who are seeing my Cartesian plane, nicely labeled and ruled out. We have our B, or the point B, and the coordinate for B is 4, 2, and the coordinate for C is 4, 4. Now I'm going to draw my vector DE, and I'm going to ask you to do some things for me. I want you to now describe in the chat, describe for me the movements that you're seeing here. And we are using the following words. We're going to state the transformation that you're seeing, and you're going to state the vector. And because we did such a wonderful job with the frog and all of that, I think it's supposed to be a smooth sailing right now. And for those persons who are still catching up, not a problem. We'll explore enough for you to catch on. All right, let's go.
So we are to describe the transformation by saying what type it is, and then do a further description on it using numbers.
Yes. Thank you, Mrs. Darby, for that backup.
All right. Jay has said something. Let us see what else will come in. Jay has said that it's a translation and that the vector is 4, 0. So the A value is 4 and the B value is 0. That's what Jay says.
All right. Anybody else supporting that?
Enrique, I can't pronounce your first name, so I'll call you by your last name. He says 4. He has not said what, he or she has not said what the transformation is, but he said 4, 0.
Okay.
Dane says it's a translation 4, 0. Enrique, you need to say what type of transformation it is.
All right, so let's look. Now, we can now look at the coordinates and compare them. So some things you're going to do. So I do agree with you. If I look at my vector and look at what is written here, my vector DE is indicating that I have moved 4 units to the right. So, and I agree with you that it's 4, 0. But let's look at the coordinates. Are you seeing my pointer over the coordinate of C? What's the coordinate for C? Can you type it in the chat? Should come up here. Are you seeing it, Mrs. Darby? I'm putting my cursor over, or my pointer over the C. Are you seeing the coordinates?
Yes, I am seeing the coordinates. I'm also, the interesting thing I'm also seeing is that the numbers are written side by side because they are coordinates, which is different from how we write our column vector.
Our vector, thank you. All right, one person stated it in the chat. Yes, you should see 4, 4. Now let's go over to, so where this is the object, and we're going over to the image. What do you notice about the coordinates for the image C prime?
So you want them to type in the coordinates first and then say what they...
Yes, I want them to, we're going to look at 2, we're going to look at C, and we're going to look at A. So I want them to write the coordinate for C, and already we're seeing it's 4, 4, and we want them to write...
over C prime so we can write it down.
Okay, it's there.
All right. J saying 8, 4.
All right, so let's go and look at A. Let's look at the coordinate for A.
So you can write down the coordinates for A in the chat and also write it in your notebook. So you have it there.
All right, yes, 1, 2.
1,
and
2,
when we
yes.
look at A prime, what are you seeing? 5, 2. All right. Now I want you to look at the coordinates. Remember, what did we say earlier? We said that this was a shift to the right, and we said 4 units. But what do you notice about the X coordinate? We notice what? What do we notice? For C, we had 4, 4, and for C prime, we had 8, 4. So what do you notice with the X coordinates? I'm seeing some things coming in the chat. Yes, yes, very good. You can see that you would have added 4. All right, so we can also use the coordinates.
They said they all go up by 4, increase by 4, add 4. Nice words to describe.
Nice words. So what do you notice about the Y coordinates? We have 4 for the C, and when we look at the coordinate, the Y coordinates or the Y value, we're seeing that we still have 4, which meant that we didn't add anything. So indeed, your vector 4, 0 is correct. Now look at how I would have I'm now changing the direction. So I am translating, or I am doing a slide, which is what this is, or a movement to the left. Can you state quickly what the transformation, I'm saying the word, but I wanted to practice it quickly. So say what transformation is, so describe the movement. Two things. Describe the movement and state the vector.
All right, Jay is saying it's a translation and vector is given as -4, 0.
All right, beautiful. So I'm going to now move, change my vector, DE. Can you now describe the translation? I already said that, but not a problem. Describe the transformation and state the vector. So everybody should be calling that word now, you know, because I just said it. Right, I think some persons are saying it. Let's look at
translation, and I'm seeing -0, 3. So that's Tony and Jay saying translation 0, 3, and Devonay saying the same thing as well, 0, 3. I think we know that as a column.
Okay, all right. Now, can you now put it all together? So a while ago, we looked at horizontal shifts and then one with a vertical shift. So now we're seeing one, we're literally moving horizontally and vertically. Can you state the transformation, or describe the transformation and state the vector? So what we want you to do.
Okay, Tony Anna said it's a translation and she has used the numbers 2, 3, although they are side by side. I think Tony understand that it should be a column, but maybe it's difficult to maneuver. Anyone else?
All right. No. All right, so now we're going to look at the line segments. Now I want you to look good on the screen. What do you notice about the length of AC? So we're going to be talking about some other properties. So right away, we are able to see how it is that we can describe one, state the transformation, and so far we're looking at a translation, and by now we are getting a bit comfortable with writing the vector.
Right,
now,
using numbers to further
using
describe.
the numbers to further describe it. Now, let us look at the line segment, or let's look at the hypotenuse. And I know we're not looking at trig, but let me point on that line segment. When you're looking at the length of AC, what we're seeing here is that the measurement is given is 3.6 units. And when we look at A prime, C prime, it's also 3.6 units. When we look at BC, we're seeing 2 units, and B prime, C prime, 2 units. Now, students, how else could we speak about these two triangles? Would you say that they are congruent? Would you describe them as similar? What say you? So these are now, we're going to be exploring some properties. And you might say to me, Miss, I don't know that word. So when we're talking about congruency, we're talking about the fact that they are the same in terms of when we look at the length, or we look at their angles. We are seeing here at angle B, the angle measure here is 90, and we look at B prime, it's also 90. When we look at the angle, and the good thing for us, what we already did, I'm not sure how many of you would have known this, the Geogebra software. Some of you can download it and explore it. You know, you guys are tech savvy. But what we did was already to insert some of this information so that we don't spend a long time doing the exploration. All right. So when we go on to the properties, you're going to see and get some information that you write down, and it's going to speak to it's being congruent or similar. So we're going to move on to that. Not sure if there's any question, and everybody clear Just want to try another one for you to see. I'm testing you. Can you just give me this description quickly? I want it in terms of the transformation, and I want also the vector quickly, because we're going to move on from this exploration. So all those persons who didn't type in the chat as yet, light it up now. We're asking you, what is the transformation that you're describing, and can you state the vector that is that facilitate this transformation? So right away, we should have it on the tip of our tongues. I know some persons probably taking a while to type. Yes, one person would have typed it in because they're quickly seeing, they're using their hands and stuff and they're tracing. One person typed in the chat, and indeed it's a translation and it's 3 units. So we're looking at A, and we're looking where A prime is. So we would have gone 3 units to the left and would have gone up 3. Awesome. Think you did an excellent job. Okay, go ahead.
Jay is saying -3, 3, and he says it's a translation. Devon is saying the same thing, and Dane as well.
All right, wonderful. So let's now continue from, and these are some points we want you to note. So again, we're asking you to write these down. So a translation is a transformation that slides. We saw a lot of that, sliding to the left, sliding to the right, up or down. So it's a transformation that slides a figure across a plane or through space. We were looking a while ago on the Cartesian plane, the 2-dimensional plane. Here are some things that we just spoke about. We did not explore, and I'm going to go back to it. We're going to look at that the translation, that all the points of the figure move the same distance. I think we explored it, but we did not nail it down. So when I say all the points of the figure move the same distance and in the same direction, and that translation does not affect the orientation, let us look back at that. Using the same example. 1, what do we notice? We notice that ABC, the triangle ABC, is facing to the left. The image, so this is our object, and our image, A prime, B prime, C prime, is facing the same direction. Wonderful. We are also seeing that A moved across -3, so we're going to the left. Tashiel, I see your hand, and I'm going to allow you to talk. Go ahead before I continue. And go ahead and unmute.
Evening, I just came back from school at class today. Miss, you said there's something that says C1, you said that is prime. So what you call the other one, like with the 2-stroke and the 3-stroke?
Okay, it just speaks to a movement or more than one image. So in this case, we have only translated this object once. You're only seeing one transformation or one translation here. If I'd gone and done it again, then let's say I would have now, so say A prime, B prime, C prime. Suppose I was translating that or moving that, that would be A2, B2, or C2, or, you know, double, as you would have said, the 2 mark and the 3 marks. So it speaks to the number of times that you're actually translating, rotating, or moving something.
Yes, Miss. What does name 3 with the 2-stroke?
So it would have meant that if I would have translated the image or the object, suppose I'm going to know, you notice that in this case, I only have one diagram here, so that one, you're not going to be confused and you can match it. If I was to draw another, if I was to do another translation of A, B, C of the object, and then putting it on the same diagram, I would have to call it another name because I'm representing a different translation. So if you're using one graph paper, suppose we should have paused and allow you to draw. Hopefully in the next one, we're going to say stop and draw this. So if I said to you, draw A, B, C, draw your object, and then I'm going to give you this translation, and I say to you, how do you name this? Because it's now the image, it's A prime, B prime, C prime. But if I give you another translation and you're using the same diagram, you're going to now give it another name. because it's representing a different movement. So you would have your A double prime, B double prime, C double prime. So let's look at this. I asked you to draw this diagram. So this diagram would be A prime, B prime, C prime. And let's say I'm putting something else. This new diagram, if I'm keeping the other one on this left, would now be a second diagram. And I will rename it as A double prime, B double prime, C double prime. And if I was to do another diagram on the same Cartesian plane, I would rename it A triple prime, B triple prime, C triple prime, or A3, B3, C3. So it's a matter of naming. And then there are sometimes in the question, you might see 2 or 3 questions there, and they're going to ask you to, and I love that point. And if we had, Mrs. Darby, if we thought about that, we would have given them one with 2 and then have them to do multiple namings in our exploration. But the thing with what we have here, I don't want to trouble and draw another one. So, okay. Yeah, but that is just a matter of naming more than one images in the actual transformation that you're doing. But and I want to say, I'm going to add something because we have a part 2 that's coming, and that's a good way to start part 2, where we do multiple transformations so that you can appreciate why we would call one A1, A2, or A3. So we're gonna explore that in our second session. So make sure you catch the second session, which will be up between now and Friday on YouTube. It will not be a live session. You just go on YouTube and you see that session. And thank you very much for that idea. We're literally going to recreate a diagram that matches that discussion, and we're going to start from there. All right, beautiful question. Love it. So in just wrapping up, we're saying that all the points on the translation, they move in the same direction and they move in and they cover the same distance. Same distance, so each point based on the translation, and they move in the same direction. Now, one more thing is that the translation is not affected by the orientation of the figure. The way in which you were labeling A, B, C, even in the image, it's the same orientation. You'll see that's a little bit more in another transformation. 2 more properties I want to leave with you. Okay, I see a hand. ZT Blake can go ahead, ask the question. Go ahead and unmute. You want me to go back?
No, it was a mistake.
Okay, go ahead, Tashel. Your hand is up.
Miss transformation, like you have reflection, rotation, and translation. Mister, you can give me a definition for transformation.
Okay, so we will get back to that. We did give a definition. It's about, so a transformation is really a change, whether it's changing in the direction, in the size of the object. So it's a change of in direction and the size or the shape. So it's a broad definition. Now we're looking at translation, which speaks to a shift. We use a vector to speak to the movement of the object. I know there are some persons who came on late and you would have missed that initial slide, but we don't want to go back. However, what we will do is at the end, we might go back to a slide, or you can always go back on YouTube.
Right, that's what I was going to suggest, that they can watch on YouTube.
Right. So we know that some persons are coming on now, because we did send the link to our schools, and we're glad that you're coming from schools and you're joining the session. All right, so the last 2 points we want to leave as it relates to the properties of a translation, that in a translation, the original object and its image are congruent. So remember, we're looking at the corresponding sides. So we said that the length of all the sides are the same and all the angles are the same, which speaks to it being congruent. And another thing we want to look at is all the line segments linking the vertices of the object and the image are congruent and parallel. So let's look back at that. Now, if we were to, and I like how this is drawn, if I was to draw a line segment, sorry, from A to A prime, and as you can see, B to B prime, which is already vertical, they're parallel. All right, so that's one of the points we wanted to bring out here. So the line segments linking the vertices in the object and the image, the corresponding vertices in the image, they're congruent and parallel. Now, here's a CSEC question for you, and this is a recent CSEC question. We would have gone through similar points. So I want you to look at this question. And it says in the diagram, the translation by which AB is mapped onto A prime, B prime is represented by which one of those vectors? Let's look at A. Let's look at the coordinate A. And I'm glad Mrs. Darby said earlier that when we're talking about a coordinate, it's written as how we have 2, 5. But when we're talking about a vector, which represents the movement, it's a column matrix as all the answers are written. So let's look at A, 2, 5.
The answers are coming in already.
Them excellent. I like it. They're
all
firing.
The way. B. Everybody is saying B.
Everybody's saying B.
Yes.
And I don't want to drag it out, which is true. So therefore, if you see, and the beauty about what we're exploring is that when you go to the multiple choice and you see areas like this, you realize that you're equipped with the information and you're better able to answer the question. So excellent. The answer is A. And my final question on this, before we go into the second segment and my other co-hosts will take over, is that you're now going to look at this transformation and you're going to describe it fully. We kept saying, and actually this question were 3 marks, you know. So when we're saying we wanted to get the 3 marks, we kept stressing, describe, state what it is. So sample CSEC question 2017. So the diagram below shows triangle RST and its image R prime, S prime, T prime after a transformation. Describe fully the transformation which maps RST onto R prime, S prime, T prime.
Okay,
we're going to give you 2 minutes.
J is first off, stating clearly that it is a translation and says that it is 2 minus 4. Tashel says 2 minus 4, but the person didn't say what type of transformation it was. Whether it was a translation or something else. But she gave a vector and the numbers are side by side. We understand how the typing goes.
All right, thank you. Thank you very much, Mrs. Darby. And let's see what would come up. Now, before I actually write the information, notice I found a point and I'm doing my checks. So I'm going 2 units to the right and some units down. And guess what? Because we would have gone through the activity about going to the left, going to the right, up or down, we know that this is minus 4. So let's put it all together. So in describing the transformation, or to fully describe the transformation that maps RST onto R prime, S prime, T prime, as what I've said before, it is a translation with vector 2, -4. You all did a fabulous job. Love the discussion. All right, so we will be now moving on to the second part of today's presentation. Oh, we have one more. Thank you for this. So let's see if we can now quickly go through this one. I didn't remember this one right here. Now, could you, this is all yours. So I'm gonna leave you with this for probably homework. So those persons who are on YouTube and the others, we're gonna give you some time to take this off. We won't get to explore this today. This is supposed to be a takeaway. So here you're going to draw the object. Well, draw the image. So draw and label triangle A prime, B prime, C prime, the image of triangle ABC after a translation T -5, 1. All right. So I'm going to leave this with you. You're going to do a screenshot. And then we're going to move over to our rotation. We're pressed for time and we have to move on quickly. We did a lot of exploring, so I'm going to move on. Hopefully you can go back and do this. We won't get a chance to go through this. We had so much rich discussion in the first part. So over to you, Mrs. Mundell Thomas.
Thank you so much, Mrs. Cameron Edwards. I was here enjoying the session and loving the rich discussion. And I'm hoping that, you know, we've made we will be able to, you know, just pick up on this discussion about rotation. Now, Mrs. Edwards, I want to share a little experience with you. You know, I was observing a tiler doing some tiling the other day, and I noticed that this is how the tiler was placing the tiles, and he seemed to be struggling, you know, to get that nice little flower pattern that should be in the middle of these tiles. You know what I'm talking about, right?
Yes.
Yes. And so, you know, I really had to just stop by and say to the tiler, you know, you really need to turn these tiles, you know, you really need to turn them so that you can get that wonderful pattern in the middle there. And that's what he did. And he was able to get this beautiful flower pattern. And you may be wondering, students, what is Mrs. Thomas talking about? Why is she talking about turning and all these things? And we're really looking at rotation. Well, you will see the link in just a few. So I'm going to pause here and give you an opportunity to look at what's happening on your screen and to describe the movement of leaf A to leaf B. So you're going to tell me what's the movement that you're seeing, or how do you think leaf A moved to leaf B? And I'm seeing a response in the chat that is quite surprising. Devonay, is it?
What is Devonay saying?
And I'm seeing, I'm guessing that should be the angle symbol, but I understand the constraints, and I'm seeing -90 degree. Okay, others are chiming in with 90 degrees. Jay saying a clockwise rotation of 90 degrees. All these fantastic things. I wonder though how they know that it's 90 degrees, because Mrs. Edwards, I haven't spoken anything about any angles, I haven't spoken anything about any direction.
Anything,
I have not even,
I
haven't even identified a center of rotation, which are some terms that will come up on. So remember, guys, before you can even say all these nice fancy things, we need to see where is this leaf rotating around? What's that critical point around which this leaf is rotating? So we're getting into the vocabulary now. All right, so I see you're off to a very bright head start. I'm getting the impression that this session will run quite smoothly. Let us see that movement again, Mrs. Edwards. Awesome. I think we can reveal what the response we have. So let's see. So leaf A was rotated 90 degrees clockwise about a specific point. Now we haven't identified that specific point as yet, but we'll talk a little bit more about what that point is and its importance. Let's move to the next one. And I want to challenge you now. I want to see who is able to describe the movement of tie A to tie B. And I'm watching the chat. All right. Devonay saying clockwise 180 degrees. Well, the degrees is missing, but nonetheless. Let's see if anyone else has anything else to add. And I have a question for Devonay after. No one else wants to describe this movement? Because Devonay has not said what it is. I only see clockwise. He hasn't said what the movement is. All right. So I see some other persons chiming in a clockwise rotation about 0.0 at 180 degrees. All right, I can't read all of them, but I'm seeing some important details coming out. Now, as with Mrs. Cameron Edwards and what she would have said during her presentation, remember when you're describing a movement, you must first state what it is. All right, so even though you know we're talking about rotation, do not take it for granted. All right, first identify what the transformation or the movement is and proceed to describe it. But I have a question. So most of you would have spoken about 180 degrees and you would have mentioned that the rotation is clockwise. My question is, if I said that this was an anti-clockwise rotation of 180 degrees about the point O, would I be correct? Let me know in the chat. Would I be correct? All right, and I see persons populating the chat with yes, yes, yes. Awesome. So remember, when it comes to a rotation of 180 degrees, whether we go clockwise or anti-clockwise, and we'll talk about those terms. You may be wondering what is Miss speaking about. We're gonna get into the nitty-gritty of what those really mean. I gather that some of you already know, but just so that no man is left behind, we will talk a little bit more about what those terms mean. All right, so tie A, as we're seeing on screen, was rotated through 180 degrees about the point O. All right. So we have talked about the Tyler and his situation. We have looked at some movements and we have thrown this word around talking about rotation. But let's see if we can get into a real proper definition of what really is a rotation. So I'm going to give you an opportunity. If you could sum up rotation in one word, what would that word be? All right, Kalisha, your hand is raised.
Right.
Go ahead. Kalisha?
It's a turn.
Okay, Kalisha says a turn, and I'm seeing in the chat, Tashelle, N3, Tonian also saying a turn. Awesome job. All right. So really, when we talk about rotation, it is a transformation. So remember, transformation is the broad heading. So it's of course a transformation, but this transformation turns a figure about a fixed point called the center of rotation. Notice the word fixed. So that point will not be moving. All right. So it turns a figure about a fixed point, and we call this point the center of rotation. All right. Now, as we look at the diagram, we're seeing a triangle being rotated. The arrow is clearly telling us the direction of the rotation. We'll speak a little bit more about that, but we're clearly seeing the center of rotation being identified in the diagram as C. Awesome. Now, Mrs. Edwards, when I thought about rotation, I was looking at several things that we see rotating about around us each day, especially now during the summer, as we're approaching the summertime. Many of us are using our fans a lot. And when I look at the fan, I'm seeing the blades rotating. I don't know why they're not rotating on my screen now, but There you go. They are now rotating. Awesome. So can anyone tell me, let's look at the solar system, because that may be easier for you to type in the chat and let me know. Looking at my solar system, can anyone tell me what that fixed point is about which these planets are turning? Anyone? What's that fixed point? What's that center of rotation? All right, I see the sun, about the sun, the sun, the sun, the sun. Awesome sauce. So we notice that the sun is not moving. It's a fixed point about which the planets are rotating. Okay, so based on the time, I'm just gonna pick a few of these randomly for us to see what the center of rotation is. So let's look at the clock. Where do you think the center of rotation would be, or where is it on the clock? If you could tell me where on the clock. You might have one on your wall you can look up at. All right, Tashel, in the center. I hear you. So could we say it's where those hands, thank you, Jay. You took the words right from my mouth. Beautiful. Where both of those hands are meet the intersection of the minute hand and the, oh, all right, great. I'm seeing some wonderful words coming out, Mrs. Edwards. The vocabulary is up on point. Awesome.
I'm seeing Cheryl also on YouTube sharing. I'm joining with Mrs. Lodge Fenton, and she's talking about the point in the middle, and she spoke about the sun earlier and the direction in which it was going.
Awesome, awesome. So as we look around, we're noticing rotation is everywhere around us, all around us. We can notice rotations. All right. Now, before we move on, Mrs. Edwards, I want to point out a very important thing here. Now, when we look at all of these things that are rotating, we notice that they are on a circular path. Did anyone else see that? Type in the chat and let me know if you saw a circular path. Look at each one of them and tell me if you're seeing that circular path that each object is on. Beautiful. I see some yeses coming out. Excellent, excellent. And it's so obvious on the Ferris wheel. Yes, as you look where we would normally sit on that Ferris wheel, we can actually see that circular path that's happening there with the rotation. And it's also very, very clear on the diagram of the solar system and also the wheels on our bicycle. Awesome. I want you to pay attention to this because the idea of the circle is very, very critical as we explore rotation. Now, how do we describe a rotation? Now, we already said when we're doing translation, Mrs. Edwards would have gone through that and she would have identified that we describe a translation using a vector. But how do we describe a rotation? Think about the definition of rotation and tell me what are some of the things you think we would need to include in a description of a rotation. Tashel, your hand was up and then it went. Are you answering the question? No?
Yes, Mr. Use degrees.
All right. So is there another word that you could tell me? What is it that we would be measuring in degrees? What would you be measuring in degrees?
Miss, the movement.
All right. So I'm gonna help you out a little bit. Remember?
Mr. Sue, warm up. Some persons type it in the chat.
Yes, I see Abby coming in. Go ahead, Miss.
It says that the direction in degrees, which is around a specific point or about the pivot or the angle of rotation.
All right, good. So we need an angle. to describe the rotation. So thank you, Tashel. You were saying degrees. So remember that degrees is the unit that is used to measure the turn, all right, or the angle. Great. So we must have the degree, but before we can have the angle of rotation, we need to identify that critical point. Remember, we spoke about it earlier, that fixed point that we were identifying in all those diagrams we looked at earlier. That is very, very important. All right, so before we can talk about what the angle of rotation is, we need to be able to identify what the center of rotation is. All right, so we need a center, we need an angle of rotation, and we need a direction of rotation. Beautiful. So let's recap that. If I'm describing a rotation fully, I need three things. Of course, I need to state that it's a rotation clearly. So describe the transformation. One, I need to say what it is. So in this case, we're speaking of a rotation. Then I must speak to the center of the rotation. Where is that? The angle of rotation. What angle is that? The direction of rotation. All right. And as we're looking on screen, we're seeing those things coming out. The center of rotation is identified with that little dot. The angle of rotation is identified to be 55 degrees. And we're seeing a direction of rotation. It says clockwise. Not sure what that means yet, but we'll talk about it in a few. Now, when we talk about the center of rotation, we already made mention of it. It's that fixed point, all right? It's the fixed point about which the object or pre-image is turning. And based on the responses I saw coming in the chat, I know you know what the center of rotation is, all right? I saw some beautiful explanations coming out. However, what I want you to also note is that the point, this center of rotation, it may be inside the shape being rotated, or it may be outside of the shape being rotated. All right, so sometimes when we're looking at transformations, we tend to think that the center of rotation has to be some point exterior to the shape, but that's not always the case. As we're seeing in the diagram here, we have a beautiful trapezium being rotated, and we notice that the point about which it's being rotated is actually inside of the trapezium, all right? And the second diagram, as we look at it, we're seeing a quadrilateral being rotated about the point O, and this point O is not in this shape any at all. But I want to point out something again, and every time I get an opportunity, I'm going to point it out, because you need to remember and understand the importance of that circular path. Let me know in the chat if you're seeing the circular path on both of these diagrams. Let me know if you've seen it, and Mrs. Edwards is hovering over the path with her cursor. All right, Devonay is seeing it, Abby is seeing it, Tony Ann is awesome. So ensure when we get into the nitty-gritty, you're gonna see how important this is. All right, so we talked about the center, and we did some explanation as to what the angle of the rotation is. We spoke about it being the measure of the turn. All right, so in our description, and as we spoke about what a rotation is, some of you mentioned some of these. So the measure of the turn is called the angle of rotation. And we're seeing in the diagram an angle of rotation of 90 degrees. All right, can anybody tell me, based on this diagram, what the center of rotation is?
Point P.
All right, I'm not sure who that was, but I heard the answer.
I think it was especially.
Okay, point P, and Abby's coming up with point P in the chat. Awesome, awesome. So I'm gonna share with you a scenario, and I want you to type in the chat your response to this question that I'm gonna share. So Sue and Roger, they were asked to make a 90-degree turn. This is where Sue and Roger are standing at the moment, and they got the instruction to make a 90-degree turn. Let's see where they are now, and you're gonna tell me in the chat who is correct. Who made a 90-degree turn? I'm seeing both of them. Someone says Sue.
Jay says Sue, both, okay.
Tony Ann says both. Okay, and you're sure? What do you think, Mrs. Edwards? Somebody saying it's Roger. Who are you saying, Miss Edwards?
I'm saying Sue.
You're saying Sue, and I'm
Yes.
saying Roger. Let's see.
Let's see.
Let's look at it critically.
So that means both.
That means both.
Right.
All right. So did Sue make a 90-degree turn? Yes, she did. Did Roger make a 90-degree turn? Yes, he did. It's just a matter of one of them decided to turn to their left and the other one decided to turn to their right. Now let's see if we can tidy up some of these instructions, because it seems to me that there was something that probably was not explicitly said in the instruction that would have helped Sue and Roger to give the turn that whoever is giving the instruction wanted them to make. So let's see. What is the direction of the rotation? We spoke about three things. Thank you so much, Dane. We spoke about the center, we spoke about the angle, and the direction. So let's talk a little bit now about the direction. So as we're looking on screen, we have an object, which is the upper red dot, and it's rotated 90 degrees clockwise. So along that red portion of the circle that you're seeing there. And when I look at this 90-degree clockwise rotation, and I'm looking at the new position of my dot, and when I look at the blue path, it's 270 degrees counterclockwise or anti-clockwise, and we'll talk about that shortly. And I'm seeing that that landed me at the same place. So this is something very, very interesting. I'm seeing here, Mrs. Edwards, from looking at this diagram, it seems to me that a 90-degree clockwise turn and a 270-degree counterclockwise turn
allows us to go at the same, end up at the same place. Yes.
Interesting things. But let's talk a little bit now about what it means to turn clockwise versus counterclockwise. And guess what? The word clock is in it, not true? So we can always use the clock to help us. All right. So we talk about a clockwise turn. This is a turn in the same direction as the turn that's made by the hands of a clock. So peradventure you're unsure one time and you're trying to remember which is clockwise again, just think about your clock and how the hands of the clock move. Once you're turning in that direction, then you're doing a clockwise turn. So what then would be anti-clockwise? And I see it popped up on screen. So anti or counterclockwise is a turn that is in the opposite direction to the turn made by the hands of a clock. So if I'm going in the opposite direction to the hands of the clock, then I am making an anti-clockwise or a counterclockwise turn. So we need to talk a little bit now about what are some of the conventions or some of the things that are used even as you go into your CSEC exam. So a positive angle, and we can use a diagram here as a reference, that 270 degrees. Right, thank you, Mrs. Edwards, for tracing that for me. So a positive angle indicates an anti-clockwise turn. A positive angle indicates an anti-clockwise turn. Make sure you write that down, because this is important. But I think some of you know it already, because some persons mentioned the negative 90 earlier when I asked about the leaf. But for those of you who probably didn't know this, ensure you make a note of it. Now, a negative angle, in this case, our 90 degree, indicating a clockwise turn. So a negative 90 degree would indicate a clockwise turn. So whenever our angle is given as a negative value, it's indicating a clockwise turn. And if it's given as a positive value, it's indicating an anti-clockwise turn. All right, let us continue. So here we are given now some addition to the instruction. So back to Sue and Roger. They were asked to make a 90-degree turn, but guess what? They're asked now for a counterclockwise turn.
Let's see who's going to change their answer.
Correct. Who is correct? Let's see their positions after the turn, miss. Awesome. So who is correct now? Sue and Roger were asked to make a 90-degree counterclockwise. And the chat is blowing up, Mrs. Edwards. Everybody is now saying Sue is correct. Awesome.
So Mrs. Mundell Thomas, it therefore means that the direction is very important in describing rotation.
Very important. And that is why, Mrs. Edwards, when we're asked to describe fully the transformation, and we see that it's a rotation, critical that these three things be included in the description. Otherwise, it's not complete. All right.
That is so.
So let's look at, we talked earlier about a positive angle indicating an anti-clockwise rotation, while a negative angle indicates a clockwise rotation. So can someone tell me then, for Roger, if I was just to put the number, the degree for the turn that Roger made without giving the word clockwise, what would I put? So I'm saying that the turn that Roger made is clockwise. Without using the word clockwise, what could I say? How could I write the angle? All right, I see Abby putting something in the chat.
Yes, they're putting in
Shell. Awesome. Negative 90 degrees. Beautiful. Awesome. So what turn did Sue make then? Because her turn is counterclockwise or anti-clockwise. And I don't want to use the word anti-clockwise right now. So how could I describe Sue's turn using the angle?
Okay, so I'm seeing positive 270 and I'm seeing negative 270, as well as a few 90 degrees.
All right. So let's talk about it again. We said that a negative angle indicates clockwise and a positive angle indicates anti-clockwise. So remember, Sue's movement was anti-clockwise 90 degrees. So I am agreeing with the positive 90 degrees. But based on our discussion earlier, Mrs. Edwards, we did say that if we go 90 degrees anti-clockwise, we could do a clockwise rotation of 270.
Right.
And it takes us to the same place.
Same place.
So I'm also agreeing with Jay with his negative 270 degrees. Awesome job, guys. So we're running ahead based on the time, and I really want you to get to the nitty-gritty of the matter. How do we rotate a shape? Critical, critical, critical. So make sure you have your pens and papers, make sure you're taking screenshots, and you may need to go back and watch this at a later time. So we're asked to rotate this trapezium A, B, C, D 90 degrees anti-clockwise about the center 1, -1. So I'm looking at this. They are giving me the description of the rotation they want. So I need to check for the three things. Do I have a center? I have a center. Go back, miss. I have a center. Do I have a direction in there? Yes, I'm given a direction. Anti-clockwise, I'm told. Do I have a degree there? Yes, 90 degrees. So notice when you're being given the question, the three things are there. So when you are describing, you must have those. All right, let's see how we go about this. So first, we need to identify and mark the center of the rotation. In this case, our center was given as 1, -1. So the first thing we need to put is identifying our center. Then we're going to be drawing a line segment connecting the center to a vertex on this trapezium.
We would want the students, though I know you can rewatch, but if it is possible that once you see us take up the Cartesian plane or a graph, just grab your graph paper, get your instruments and begin. Because remember, we did say from the initial state that you need your instruments. And a part of this session is to get you to practice. So if you have your graph paper, we know we are running behind, but we still want you to be practicing. So while we move on, make sure you have your instruments. Go ahead, miss.
All right. So we're drawing our line segment connecting a vertex. And in this case, we have chosen A to start with. All right. Notice if you're looking on screen, you would have seen where we have connected A, which is the vertex we have chosen, to the center of the rotation. Now, what's the next thing I need to do? Remember earlier we talked about the importance of this circular path. Here it is coming right back at us. So we need to draw a circle or an arc using this line segment that we have from the center to A as the radius. Look at it. It looks like a radius, not true? Yes, man. Coming from the center of the circle. And of course, there it is touching that point on the circumference. Beautiful. Now remember, we said that each point must make that circular path. It must take that circular path. Therefore, wherever I'm going to put the image of A, wherever I'm going to put A prime, it must lie on the circle that's here. So depending on the degree and the direction, so depending on the angle and the direction of the rotation, then that will determine where on this circle A prime will lie. So let's go. So I'm gonna align my protractor properly. Notice the center of my protractor is right at the center of rotation, and I have aligned my line segment with 0 on my protractor. Now we were asked for a 90-degree turn anti-clockwise. So remember, we're going in the opposite direction of the hands of a clock. Can I see my 90? Oh yes, there it is. I've marked it off and I've connected a line segment. Now notice that even though my line segment is extending beyond the circle, notice where A prime is. So look at it. Let's talk about this because this is also important as we're going to get into the properties. Question. The distance from the center to A and the distance from the center to A prime. What can I say about those two distances? Is there anything about them that jumps out at you? I wonder who can tell me. All right, someone says they are equal, they are similar. Kenarda says they are both radii. What is going on here? We have some critical thinkers. Are you sure, Tashela? You may want to check. You may want to check that what you said about parallel. Just double check that one. All right, but do you agree that from the center to A is a radius? And from the center to A prime is a radius. And what do we know? Yes, man. If we have radius in the same circle, then they must be equal.
So someone on YouTube is agreeing with you that they're both the same.
Thank you for that, Mrs. Fenton. Thank you. All right, awesome. So one of the things that we should notice here then is that the distance from the object to the center and the distance from the image, which is A prime, to the center must be the same. Critical, critical, critical. All right. So guess what now? If I'm rotating the shape, I would need to do this with all the other vertices. All right, Jay, I see you responding to Tashel. Awesome. I need to do this for all the other vertices. All right, so we have already done it for A and A prime, so we can put those in. We did that earlier, and we're sure that that is 90 degrees. We did measure it earlier. Now notice B and B prime. What do you notice about them? Are they on the same circle? Look at them. Good, 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 good. B and B prime. Are they on the same circle? Wait, I don't see the chat blowing up. What's going on? Oh, Devane. Oh, you heard me wonder and wonder. Okay. Awesome sauce. Great. So remember, and you see how many times I'm going to say it? The circular path is very important. All right. So notice B has taken a circular path, and look where B prime is, right on that circle. Can we agree then that the distance from the center to B and the distance from the center to B prime, would those also be equal? And for the very same reason that we said earlier, they would be radii of the same circle. Beautiful. So we can allow the animations to come in, Mrs. Edwards, and for us to see those 90 degrees coming out as we connect each image point to the center and object point to the center. Very, very important. Very, very important. Notice each point and its image are on the same circular path. Great. So this is how we rotate a shape. Now, before we get into the properties, let us examine a couple of other things. Let us take a look at even how this shape is labeled. So let's look at some similarities that we're noticing. So Mrs. Edwards, maybe you can assist me with the cursor. And as I'm asking the questions, can anyone tell me what's the length of AB, the line segment AB? All right, and Dane is fast out of the blocks. All right. Anybody wants to contest Dane's answer? He says 2 centimeters. Is there anyone who disagrees? Is there anyone who agrees? Devane says 3. All right, someone else agrees. Let us do the jumps, miss, and see. So from 2 to 3, that would be 1 unit. In this case, we can say centimeter for now. And another, good, Devane, see it now, good. So it's 2 centimeters or 2 units to be more general. So let's look at A prime, B prime. What's the distance there, or the length of that? Same 2 centimeters. All right, I see the chat blowing up. Awesome. So, and if we were to explore each of these sides, if we looked at DC and compared it to D prime, C prime, you would see that it's the same length. If we checked AD and looked at A prime, D prime, we would see that it's the same measurement. So Mrs. Edwards used that word earlier when she looked at translation. Whenever we saw shapes that were identical to each other, the lengths were the same and the angles were the same. Anybody remembers that word? Shadi, and you're going on with things. All right, Brianna, I see your answer as well. Congruent, awesome. So one of the properties, therefore, of a rotation is that the object and the image would be congruent, all right? Now they may turn slightly different because when I'm looking at this, I see AD, which was a vertical line segment on my object. And then when I look at A prime, D prime on my image, I'm seeing that it's horizontal. All right, so the shape, we expect this, you know, because we said rotation is a turn, didn't we? So we're expecting some turning to take place, clearly. But let us look at the labeling and see if that can tell us anything as well. So let's look at our object and let's go anti-clockwise. Thank you, Miss Edwards. I see you doing it. So we start, we have A, B, C, D. That's anti-clockwise. Let us check our image. Are we going anti-clockwise and see if we're getting those same thing, or is it in any other way? Let's check. A prime, B prime, C prime, D prime. So we're getting the same kind of labeling. So we went anti-clockwise, we got A, B, C, D. We went anti-clockwise on the image, we got A prime, B prime, C prime, D prime, all right? So though the shape is turned differently, we're seeing that the labeling is pretty much the same, all right? As we go in a particular direction. So let's just put all that we have said so far together. So every point on the object makes a circle around the center of rotation. And I don't know, I must have said this so many times already, but it cannot be overemphasized. All right, so every point on the object or pre-image makes a circle around the center of rotation. The distance, note this, from the center of rotation to any point on the object, otherwise called the pre-image, is the same distance from the center of rotation to any corresponding point on the image. And we talked about it earlier. And we did say we expected that to happen because they would be radii of the same circle. All right, awesome. Let's continue. All right, and we did this one just now. An object or pre-image and its image are congruent. And I know you know what that means because we talked about it just now. But we noticed that the figures may be turned in different directions. We don't watch that because we expect that to happen because we said rotation is a turn. You told me that's the one word you would use to sum up a rotation. All right, so let's continue. Now, so far, we have looked at situations where the center of rotation was not the origin or not 0, 0. Let me make sure I say it so that if you didn't know that that's what we call the point 0, 0, you know it now, the origin. Now, when the center of rotation is the origin, some wonderful things happen, some excellent patterns come out, and we couldn't end a session today without sharing with you what are some of the things that happens when our center of rotation is the origin. So in this diagram, I know we usually label it O, we have labeled it D, no problems here, we know it's noted there with that blue dot. Great. So let's talk about an anti-clockwise rotation of 90 degrees about the origin. Nice for us, we have an object in blue and we have our image in red. Now we're gonna do some comparisons. So you're gonna have to look closely as we compare the coordinates for our object with the coordinates for our image. All right, so let's go. So A was 2, 4. And it mapped to A prime, which is -4, 2. Let's see what happens with B. B was 6, 4. And it mapped to B prime, which is -4, 6. Let's look at C. C is 2, 6. And C prime is -6, 2. I'm laughing because I'm looking in the chat and someone is racing ahead of me, Mrs. Edwards. All right, Tashel,
I'm looking.
I see what you're saying. Let us see if what you're saying is so. Let's see. Can anybody else? So I get your answer already, Tashel. Can anyone else tell me what they noticed? This might be a little bit lengthy to type in the chat, perhaps. So if you would like to unmute, you can let us know. And we'll allow you to share. What do you notice? What's happening here with these coordinates? We're seeing a pattern. You seeing it, Mrs. Edwards? I am seeing a pattern.
I'm seeing a pattern too.
Jay says swap the X and Y value and then invert the Y value. Sure, it's invert, I want to say. Okay, so I see XY mapping to -XY. You're sure, Devani? Let us check. So let's see. Let me run with the swap that Jay says. So he's noticing that some interchanging is taking place. So what was the X is now in the Y place. All right. So what's in the X? So we had 2 in the X for the first one, and it's now in the Y place. Let's look at what happened with what was in the Y. We had 4 in the Y place for the first one, and then it's in the X place, but it's not 4. It is the negative of it. Interesting. So these are some things. You may want to take a screenshot of this. You may want to go back to the video to watch it just to ensure you catch all of it. But I want to ask you, I'm throwing this out there because I want to know if you get this. So I have a point, and my point is coming up on screen. And you're going to tell me, if I rotate this point 3, -5 in an anti-clockwise direction of 90 degrees about the origin, where or what would the coordinates for my image be using what you have noticed here? What would the image be? Right, I see Tashel typing in the chat. I don't know if she's correct yet, I need to see more answers before I determine if she's correct. 5, 3 positive. Okay, 5, 3. All right, I see 4. All right, about 5 persons. All right, so the chat blowing up now.
It's blowing up.
Okay. And I'm seeing the correct answers coming out. I'm seeing the correct answers coming out. So yes, we saw the 3 moving over into the Y place, and we saw the negative of -5. In other words, +5, where X is. Awesome. So let's run along. How about if we performed a rotation of 180 degrees about the origin? Let's see if we can pick up some nice patterns here again. So I'm just going to allow them to come up in the interest of time. I'm going to allow the coordinates to pop in one at a time, and you examine them and see if you can tell me what's this relationship that you're noticing. All right, so we had 2, 4, and it mapped to -2, -4. We had 6, 4, and that mapped to -6, -4. All right, I didn't even realize the chat was already blowing up. So I see Tashel and Devani giving me responses in the chat. Still waiting on some others. What do you notice? Someone else, Enrique, said the sign changes. All right, I get what you're saying, Jay. Don't think you're using the right word though, but we're seeing the opposite values, okay? Or we negated the values, all right? All right, Tonian, I don't really want you to say the X and Y values are negative, because guess what? I'm gonna give you a point because I want to know if you catch on to this, because I don't want you to say that they are negatives, because what if they were negative before? What would happen to them when I rotate them 180 degrees about the origin? Would it still be negative? So be very careful. Remember, we're looking for a generalization. All right. So be very careful. Yes, Mrs. Edwards.
I was wondering if I should bring up the point before the generalization, but the it's good.
No, man, go ahead.
Okay.
Because we're gonna use the generalization now. So I'm hoping that I'll hear from Tony, and I'm hoping I'll hear from Tony and the response for this particular one now. So we have 3, -5, and using what we have noticed, if I rotate this point 180 degrees about the origin, what would the image coordinates be? All right, I see an answer. All right, I don't see Tonian yet, probably she's still working. All right, here she comes in, beautiful. So you see Tonian, why you can't just say the X and Y values are negative, right? So what you can say is that the X value, whatever it was, it would now be its opposite. So if it was positive, it would now be negative. If it was already negative, then it would be the opposite of that, which would be positive. All right, awesome. Now remember, guys, I'm going to stress it again. These things only happen for this specific center, meaning the origin, and for these particular angles, all right, and direction. Make sure you get that. So it's not every rotation. Notice the heading. All right, so we're going to look at the last one as we look at this pattern thing. So we're looking at an anti-clockwise rotation of 270 degrees about the origin. And again, I'm going to let them just slide in the interest of time. And you will tell me, what do you notice? You're sure, Devani? So let's take our time and look. I know we have gone over the time we said, but this is very important, all right? And we don't want to leave you without the tools that you need, all right? Devani said, sure. Okay, we make mistakes, I know. And sometimes our fingers touch the wrong thing, you know, I can tell you. All right, so let's see what's happening here, Mrs. Edwards. So we noticed here that yes, some swapping did go on. Let me steal Jay's words. Some swapping went on, but we noticed in this case, when our X value was moving over into the Y place, it didn't just move there. It was what? It's the opposite. All right, so look at the questions that we had. When 2 was there where X is, in our image, we didn't have 2 there where Y is. We had a -2. All right, so we have to pay attention to these things. All right, so if I have a point XY, my image point under this specific rotation, anti-clockwise of 270 degrees about the origin, then I'm going to have my X value will change its sign. And then of course we'll have them interchanging places. All right. So again, same point we're doing 3, -5. Let's see, what would my image point be? I saw some things in the chat that weren't so right. So let's check this one. So we had 3, -5. Now, based on what we saw in the pattern, that X value needs to become its opposite. In other words, it needs to now be a -3.
That's
and
not what...
then they are supposed to interchange.
So they're not noticing the opposites, and we want them to really pick out that on that, because I noticed that they're typing in, but where the signs are concerned, they're not. I've seen a lot of the swap and all of that, but you need to make sure you see and look at the signs.
Awesome. So congratulations, Dean and Jordan. I think you two had it correctly. So remember now to check on these things, and I'm going to say for the last time, these things happen only for rotations of these particular degrees and directions when the center of rotation is the origin. Awesome. So I think we have one more section, Mrs. Edwards.
Yes.
So we looked at how to rotate a shape. We looked at some patterns that happened. And next up,
we're trying to
look at how to identify the center or how to describe, let's just put it like that, how to describe fully
a rotation.
Now you might be wondering, constructing a perpendicular bisector, what is that doing in a presentation on rotation? You'll understand in a few, because you will need this information in the next part that we're going to look at. Well, you may need it, let me put it that way. All right, you will definitely need to understand the concept of a perpendicular bisector. All right, but they are going to construct it using your compass, your pair of compasses, or you're going to draw it with your protractor is another story, but we tuck this in there so that you have this under your belt, so you can choose to use it. All right, so if we're constructing a perpendicular bisector, I think this probably should have been after, but let's do it here anyway. How do we construct a perpendicular bisector? So I want to bisect, draw a perpendicular bisector of that line segment connecting A and A prime. Notice my compass here, it's opened to a radius that's more than half the length of the line segment. Very important. All right. Now, having done that, I'm using A in this case as the center, and I'm going to be scribing my arc above the line segment in this case, and I'm also going to scribe an arc below the line segment as you're seeing on screen. Now, I cannot change. Remember now, you can't adjust. So this is a little construction too, because guess what? You might get construction on your exam too.
Yes, they might get construction.
Take it this, you might not necessarily need it for your rotation, but let's see, we're arming you well. So let's look now, you can't change the radius, meaning you can't adjust your compass or open it any wider or narrow it. No, you have to keep it as is. And you're gonna now use A prime as the center. All right, so let's see our compass moving over to A prime. All right, that's our center now. And we're gonna again scribe an arc at the top. Notice my arcs must meet each other. They must intersect. That's critical. And that is why you have to ensure that you open your compass to more than half the length of the line segment. Awesome. Now, once we have done that, we simply remove our compass and we draw now our perpendicular bisector. Remember, a perpendicular bisector does two things. One, it cuts the line segment in two equal parts or in halves, and it does so while forming a right angle. All right, so let's see how this becomes important. So based on the time, I am respectfully asking for 15 more minutes of your time. I know we had a particular time frame within which to operate, but the discussion has been so rich and you have been awesome students. So do I have your permission to continue for another 15 minutes and then we'll just wrap this up? So let me know in the chat. Beautiful, thank you so much. Awesome. So how do we find the center of rotation? So here I have triangle ABC and I have triangle A prime, B prime, C prime. Oh, this has been rotated for me already. Wonderful job. But I need to describe it. So one, I know it's a rotation, and we'll talk about the fully part in a few. But for now, we want to find the center of rotation. How do I do that? Let's see, Mrs. Edwards. How? Jay, hold on, you're using too much big words. Extrapolate. All right, so let us see how we find the center of rotation. All right, so we're going to use a line segment to connect a pair of corresponding vertices. So I'm choosing A and A prime right here. All right, so you can choose another pair if you so desire. We have started with A and A prime. What am I going to do with this line segment? Let us see. Here comes the clincher. Draw the perpendicular bisector of the line segment. Now remember, I said you would need the information I just did before. That's one way of doing it. But guess what? You could also use your ruler and measure the line segment from A to A prime and find the halfway mark. And then use your protractor and measure and draw a 90-degree right in that midpoint. Of course, that option is open to you because this is not a question that tests construction in particular, all right? But the most important thing is that you must have the perpendicular bisector of the line segment as we're seeing on screen. But guess what? You're gonna have to do this again, you know. Yes, man. Remember when we rotated the shape, we had several circles that all had that same center point? Yeah, man. If you missed it, you're going to have to rewatch this, you know. But yes, remember that. So that's what we're doing here. So we are constructing or drawing our perpendicular bisector for B to B prime, that line segment. Let's put that in, Mrs. Edwards. All right. Here is our perpendicular bisector for B, the line segment from B to B prime. And we can set it for 2, but you could do C and C prime if you so desire. All right. But once these two are accurately done, wherever they meet will be the center of rotation. All right. Who can tell me the coordinate for this? What's the coordinate for the center? Because you may be asked to state the coordinate for the center. What's the coordinate for the center? All right, so we have students who are thinking. All right.
Yes, we are.
All right. I like that.
And likewise on YouTube too.
Awesome. So my center of rotation here is 0, 1. Beautiful. Let's continue. So now that I have my center of rotation, I can easily find my angle. That's the easy part, not true? Yeah, man. So let's put in our center, and then we're going to be connecting line segments from a point on the object to the center and a point on the image, corresponding point, of course, to the center. In this case, we have used A and A prime. What do you think we're going to do next? Yep, we're going to use our protractor to measure the angle that's formed. Do I have a protractor on hand? Of course. All right. So who can tell me what angle that is? And of course, you're going to have to tell me direction, you know. Because if you're going to tell me the angle, as long as it's not 180 degrees, where the direction really so, yeah, you're going to have to tell me direction. So who can tell me? All right, Dane says 90 degrees anti-clockwise. I wonder if he's correct. Does anyone agree, disagree? Devonay is agreeing. Do I agree? Yes, I'm agreeing. Don't watch my face. I am agreeing. All right, awesome.
I'm agreeing as well. I'm agreeing.
Awesome. All right. We can move on. So this is our last thing, we're gonna use up what we have learned so far about rotation. This is an actual CSEC question, January 2017. The graph shows triangle DEF and its image D prime, E prime, F prime after a transformation. Describe fully the transformation. Please circle that fully for me, Mrs. Edwards. Describe fully the transformation that maps DEF, that's triangle DEF, to its image, triangle D prime, E prime, F prime. So first I'm gonna ask, what is the transformation? Let me see it in the chat. What is the transformation? Dane says it's a rotation. Somebody else a
Mrs.
rotation.
Mrs.
Yes.
Thomas, I'd like somebody to tell me how they know it's a rotation. What is it that you see?
Getting there. Yes,
Okay.
man, I was about to ask. So let's see. Who shall I choose? Who is volunteering?
So the question on the in front of you now is, what did you see? What do you notice? What other word would you use to let you know that it is? Yes, you use a visual inspection, but when you inspect it visually, what did you see? Tell me another word other than rotation that I could quickly associate with it to know that it is a rotation.
Tashel says she saw that it turned, and N3. All right, Jay speaking about orientation. So remember some of the things that we said you can look at, you can look at the labeling. You can look to see if was it a slide. If it is a slide, then you know it's not a rotation for sure. It must be a translation. All right. Okay, so we saw some turns coming out. So you have to closely inspect. Yeah, I hear you, Dane. You did visual inspection first. I'm cracking up over here with your statement. But it's true, you did visual inspection, but what did you notice? Somebody said they noticed that the shape turned. All right, so we saw, and I remember earlier we looked at something, because we compared some line segments. So we could even take one of those. We could take FD, and we saw that FD was a vertical line segment. Hold on, Mrs. Edwards. We saw that FD was a vertical line segment. And then we look at F prime, D prime. We notice it horizontal. So that, no man, it can't be a slide. Some turning going on. Yes, Mrs. Darby, I see you're unmuted.
No, I'm right. I was going to agree with you that I just look as you say it, I see it. FD was upright, vertical, and F prime, D prime turn crossway.
That's right.
One of the takeaway then coming from
crossway, turn.
So coming from the translation, you clearly see that this is not any slide or any push or any movement horizontally, but this turn. That one word that the students had used earlier to describe the rotation, there is a clear turn.
Awesome job, awesome. So now that we have identified that it is in fact a rotation, tell me now in the chat, what are the things that I need to describe fully a rotation? The chat should be blowing up, Chat should be blowing up, but I know you need time to type. So let me give you some time. What are the things that we need? All right, Dane says the direction. Not alone, Dane. What else we need? All right, I soon respond, Dana, because you would have given a full description. But for now, I want to know what are the things. All right, so we need the angle. I'm seeing that coming out. The direction, and I'm seeing the center. Awesome. But guess what now? Which of these do you think we would need to identify first? All right. So
they're firing.
The center. Good. Because if I'm going to do any measuring of any angle, I need that center to be measuring. All right, so let's see if we can go ahead and identify these 3 things, and then we'll be done for the afternoon. All right, so let's go ahead, Mrs. Edwards. So remember, for our center, we need to connect 2 pairs, or a pair for now. Let's start with 1 pair, E and E prime in this case. Connect them and find or draw the perpendicular bisector. All right, so we'd have done that for E and E prime, and we're also doing D to D prime, that line segment. We have constructed or drawn the perpendicular bisector. What am I to look for? Now that I've drawn these, what should I be looking for? What is this gonna tell me? How am I gonna find this center? What am I looking for? The intersection of what day? I'm gonna have to be a little bit more specific. Intersection of your shortest point, E and D. So let me help you a little with your vocabulary. So what are we looking for that should intersect? The perpendicular bisectors. Good. Thank you, Jay. The perpendicular bisectors. Awesome. All right. So where are they meeting here? Where they intersect?
We could ask them at the coordinates for that intersection.
All right. Let's say at the origin. All right.
And then there, 0, 0. Right.
Awesome. All right. So we have our center. So next we need our angle and direction. Let's continue, Mrs. Edwards. All right. So remember, once we have found our center, we need to connect 2 corresponding points to the center and then do our measuring. So we didn't allow the protractor to come in here. However, once we recognize that it's the origin, we probably can do a little checks based on the pattern. The word will come back, Tashel. Based on the patterns that we explored earlier, we can do some checks. So we look at D and we see that is 1, 2. That's the coordinate. And then we look over D prime and we see that it's -2, 1. And we can think and say, oh yes, I remember now, yeah man, there was a pattern that we noticed when we had an anti-clockwise rotation of 90 degrees, you know. Yes, man, I remember it. So notice now it's on a Cartesian plane, and so we may be able to explore using the coordinates. Of course, I'm not telling you not to use a protractor. No, I'm not telling you that. So your protractor is a useful tool. You can also use it here to measure, and you will, of course, in this case, get a 90-degree anti-clockwise rotation. So let's put it all together now. Describe fully. So what are we gonna say? What's the transformation that maps DEF to its image D prime, E prime, F prime? It is a rotation. Check.
I'm waiting to see what they say in the chat.
What else? Give me the rest. All right, it's an anti-clockwise rotation. All right, 90 degrees about the origin. Thank you so much. All right, we can bring it up on screen now, Mrs. Edwards.
Okay.
All right, awesome. Awesome job, guys. I hope that you would have learned a lot from this session and you would have been equipped with important tools that are needed for your upcoming examination. So we're just gonna show you a little, summary on screen while the link for the evaluation form will be posted in the chat. Please feel free, not feel free, let me fix that up. Please ensure you click on the link and evaluate the session so that we know how we can better prepare to help you in any upcoming sessions, all right? Remember the name of the presenters, those will come up on screen. So you should be able to select the persons who presented. So that will come up in a few. So remember, final thing, rotation is a transformation that turns a figure about a fixed point. And if we're describing this, ensure we have our center, our angle, and our direction of rotation. Thank you so much.
All right. Mrs. Darby, you want to come back in and just do our thanks and then allow them to do the evaluation.
Right, so the presenters are on screen. So please click on all these 4 persons when you're completing the form.
The link has been placed in the chat already?
Yes.
The evaluation link, okay.
Yes, it was
placed.
All right. So, students, we are happy that we could accommodate you today. Your exams is just a few weeks away, so this will give you some time to go back through the presentation. Remember that the presentation is available on YouTube, along with the others that we had done earlier. We did some, I think, last month.